Okay, so what we will do today is that we have started learning the what we had finished till few relations, right? Like few properties we know how to write the enthalpy and entropies at various stages, like when we were under the dome, when we were outside the dome, and various points we have considered, and we were able to write the what the relations for what enthalpy and entropy. So now let us move from that point onward. So let us understand few more diagrams. So let me move to here. Okay. Okay. So I'm trying to help you various property diagrams. Few property diagrams we have seen. So let me draw you few more property diagrams. Okay. So first is on TS scale. How do you show all these phases? Because we know that there are three phases, right? So on TS scale, how do we see that? Is we have one solid state, and this is your solid state region. And then we have liquid region, and this is solid. This is solid plus liquid. And then we have liquid region. This diagram we have seen, right? So this is liquid region and this is vapor region. So this is liquid plus vapor region. And this becomes what? Vapor region, right? So beyond this point, there is vapor only. So this dome is not continued till this point. Like, let me erase this one. Okay. Yeah. So this is your diagram for whom? TS diagram, right? And we can see that here also we have solid region, and then we will be having solid plus vapor region also, right? So this is the region where we have solid plus vapor also. This is your region where we will be having solid and plus what? Vapor. This is solid, and beyond this region we will be having vapor. This point onwards you will be having vapor, right? So this is what property diagrams are helping us to know. Okay. Let us next draw the same diagram on PT curve, on pressure and temperature axis. So if this is P, this is T, then on PT diagram, what will happen that let us say that this was the region where we had solid, and this is the region we are having vapor. Then tell me that will there be any phase change present? Here we can see that all of the phase changes are visible. But here the phase change will be considered as a point. Why? Because whenever we are undergoing any kind of phase change, then pressure and temperature are dependent properties, like pressure as well as temperature remains constant. Then how I will show, like there is only a point where both of the things can remain constant. Otherwise, if I draw the line like this, then this axis is constant. That means pressure is constant, but temperature is varied. If I draw vertical line, that means temperature is constant, pressure is varying, right? So this is not possible for any line to happen like this. That means that this will be a point only. And then what we will have, that we will be having one liquid region and one vapor region. Here your phase changes are absent. So the questions comes into the manner like that, in which of the following diagrams phase changes are absent. So what you would say is that in the what PT curve or PT diagram, we can see that there is no phase change visible. Why? Here there is phase change, but this is not visible for you. Okay, so phase changes you cannot show them here. Okay, and this point is called what? Triple point. Triple point. So can you see that triple point is a point on PT curve? So questions keep on coming like this, that in which of the following diagrams your phase changes are absent, your triple point is a point. Here also we have triple point, but triple point we can see we have a line also. So here your triple point is a triple point line, and here what we can see is that here triple point is a point only. Okay, and TS curve we have already seen. This we have seen on the what magnified scale, like liquid plus vapor region and vapor region only. Why? Because we are not much worried about that what happens with the solid and these phase change regions. Okay, and if I draw, yeah, this is the more important, like TS and PT are mostly serving our purpose. So we are always interested with whom TS and PT curves, and sometimes PV curves are also important. So let us try to understand them as well. Okay. So next is what? PV curve. So how PV curve like looks like? Next is, this is your TS, this is PT, and next is pressure specific volume diagram. Pressure and specific volume diagram. Okay. So how does it look like? Pressure specific volume diagram. Okay, so this we have understood, right? So here what we had, solid plus liquid, solid plus vapor. And beyond this region, what happens? There is vapor region, there is solid plus vapor. So in pressure volume diagram, if I draw again it with the magnified scale for pressure specific volume diagrams, then how it would look like? It is then see, one thing you will have to make what constant, like you will be varying few things and you will keep one thing constant. So here what you are trying to do is that you are trying to draw isothermal lines. So how does it look like is that this is your isothermal line. You have started from some point and then this has gone like this. Okay, and similarly your different curves would look like this one, and these are what temperature is equal to constant curves. Got the idea? So this is the point where what will happen, that your curve would look like something like this. Okay, so this is what called critical point. Okay, and at critical point, at critical point, sometimes this kind of questions come into exam. So we have seen at critical point what happens, that dy by dx, you know that dy by dx, what happens, this is equal to 0. And what about del square p upon del square v, del v square, this is equal to what? This is also equal to 0, but this is single derivative, this is double derivative, and the triple derivative would be less than 0 at the critical point. So this will be less than 0. So this is your pressure specific volume diagram. This is your property diagram for whom? On what axis? On temperature and entropy axis, on pressure and temperature axis. Okay. And there is one thing which is very important, like we have seen the substances. What is the nature of general substances? That if you cool them from, or let us say that if you have solid region, then from solid to liquid, what happens, that most of the substances expand, but we have one water in our exception, that from solid to liquid it will what? Contract. Solid to liquid, see, for general substance, like water is an exceptional case. For water, what happens that if you are changing liquid into solid, then what you will feel that it has got expanded. Okay, but for general substance, what happens? For general substance, what happens that liquid to solid, we will feel that it has got contracted. Okay, and for water, what happens from solid to liquid? It gets what? From solid to liquid, for water, it contracts. And for solid to liquid, for general substance, what happens? We have seen these things in nature. Na? Then from solid to liquid, it would expand. So the curve which we have drawn, PT curve now. So what it would happen is, for PT curve, for general substance, we have drawn something like this, right? Okay, this is your solid region, this is your liquid region, and this is your vapor region. Just now we have seen. So what happens that delta P upon delta T for general substance, for H2O, and for general substance, we'll have to look, then we will decide that what nature of this curve will be, right? So we have seen for water, this is less than 0, and for general substance, it is greater than 0. Then what will happen? For water, the curve will look like this one. This is for what? This is for water. What the idea? And if there is a question which keeps on appearing in the exam, that this is your triple point pressure and temperature, right? This point has, this is your triple point pressure and temperature. So what is this value? This is, the pressure value is 0.61 kilopascal, and temperature we know that it is 0.01 degrees Celsius, right? So if you are below the triple point temperature or pressure, then what will happen? Or more specifically pressure, that if you are below the triple point pressure, then what happens that you are lying in these regions. So here what will happen that your solid will directly get converted into what? Your solid will directly get converted into vapor. So this is called what? Sublimation. Solid has directly changed into vapor. This is called what? Sublimation. What the idea? Let us try to understand few more things. Then we have one very important diagram called Boyle diagram. Okay. So what this diagram is, that this is drawn for on which scale? On HS. So this is an HS diagram. So here again you will be having what? You have liquid region, you have vapor region, and you have liquid plus vapor region. So what happens here is that what you are trying to do is that you are trying to draw some constant pressure lines. Then what is the nature? Is that constant pressure lines are, what do we see? That constant pressure lines are straight line in this region, and here what do we see is that they are the lines with increasing slope, or not lines, the curves. So what is the important of this curve? Let us try to understand. You have one important relation called TdS is equal to dH minus VdP. Okay. So if you are drawing into this region, in the phase change region, then what happens that pressure is constant, or more specifically, like we are trying to draw the constant pressure lines, right? So for constant pressure lines, can I do is this one, that TdS is equal to dh, then the slope of this curve, like dh upon ds is giving you what? Temperature directly. So sometimes if you don't know the temperature, that at what temperature you are working upon, then what you would do is that you will go into which diagram, Euler diagram, and then you will look after what the slope of this curve, and the slope of this curve is directly giving you what this temperature is in Kelvin scale. So this is nothing but absolute temperature. Okay. And provided dH upon ds when the pressure is constant. Okay. And what happens is that if we are talking with this region, like in the phase change region, we have seen this one now. In the phase change region, what happens is that pressure and temperature are dependent properties. Then if P is constant, then T is also constant. Why? Because these are constant pressure lines. So the temperature will also remain constant for this one. So can I say that slope of, if see, this is the slope of what? The HS diagram in wet region, then can I say that if temperature is constant in this region, then this slope is also constant? Yes, I can say slope is also constant in which region? In phase change region. Yeah. And what is more important to remember, that we are trying to draw constant pressure lines on the HS diagram, and constant pressure lines are, these are straight lines. These are what? Straight lines. Straight lines in the phase change region, and these are curves with increasing slope. Curves with increasing slope. Here your slope was constant. Here your slope was constant. So let us come to the question part. So what kind of question comes into the exam? They would simply ask you that what is this diagram drawn on? First, they might ask you that what is the slope of this curve? Second, they might ask you the slope is constant or varying. Third, they can also ask you that the slope is what? In this region, this is constant, then what about this region? So many questions from one diagram. So we have seen all of them. Okay. Next. Now let us understand thermodynamic relations. The properties chapter is closed. Now let us move to whom? Thermodynamic relations. Yeah, this class we will be probably finishing this this thermodynamic relations is the last topic, and then we will probably take one class where we can do some problem, and we can also work upon applications parts, right? Like we have seen various process and everything. So what we can do is that we can extend one class and we will learn the applications parts where the questions are keep on appearing in the exam. Okay. So this is basic thermodynamics, and we'll try to apply it to different cases. Okay. So thermodynamics relation, one important, very important relation is Gibbs function. So let us understand Gibbs function. Directly they would ask you that what is Gibbs function. So what is Gibbs function is G is equal to H, which is enthalpy, minus Ts. This is Gibbs function. And what is the important point about Gibbs function is that for all the real process, Gibbs function is 0 and attains a minimum value at the equilibrium. Like if you are you are trying to work in the equilibrium conditions, then you will have to look after that has your Gibbs function value is at the minimum value. Then what I would write is that for real process, for all the real process. Okay, before understanding this one, let us understand Helmholtz function also. So So what this function says, this says that F is equal to U means internal energy minus Ts. So this is H minus Ts, Gibbs function, Helmholtz function is F is equal to U minus Ts. So what it says that for all the real process, the value of this Gibbs function and Helmholtz function will be always 0, and it will attain a minimum value at what? At equilibrium conditions. Next. And we have seen numerous times the questions have been asked from this statement, which I am writing, that degree of completion, degree of completion, rate of reaction, direction of the reaction, direction of the chemical reaction, these are all decided by whom? These are all decided by whom? Second law of thermodynamics. Or if you have no option, then what you can choose is that you can choose this is decided by whom? Gibbs function also. Okay. Like this is decided by second law of thermodynamics. Why? Because we have seen that what is the, like we have seen now that these are the direction and all things were decided by whom? The second law of thermodynamics. But sometimes they don't give option like that. They will be assuming us to know that Gibbs function is the one who is helping us to decide these factors. Okay. Okay. Now we have four important relations called Maxwell equations. So what are these Maxwell equations? So Maxwell equations, one thing very important, like if we know this from mathematics, like if I write dz is equal to m dx plus n dy, then if this is exact, then it has to follow this relation that del m by del y when your x is constant is equal to del n by del x when your y is equal to constant. Like if this is your exact equation, what? That this is an exact equation, exact differential equation. So one thing very important to understand Maxwell equation, we need to understand this one from mathematics. And there is one important relation, like if z is the function of xy, then I can write that del z upon del x when your y is constant, and then del x upon del y when your z is constant, multiplied by del y by del z when your x is equal to constant. The product of these three is -1. Sometimes they can ask you this relation also. So these two things we need to understand. These two things we need to understand. Okay. Then Maxwell equations, will derive them one by one. So we have four equations which will help us to determine this Maxwell equation. So first is, we have seen that one relation we know. First, this is your first Maxwell equation. What is that? That TdS is equal to du plus pdv, we know, right? So if this is an exact equation, then how I would write that du is equal to TdS, du is equal to TdS minus pdv, right? Then using this relation which we have discussed earlier, like this is now an exact equation, then this relation will be followed. Then can I write down that delta t upon, like let me write down once again that this was dz is mdx plus ndy, right? then we can write del m by del y at x is equal to constant is equal to del n by del x at y is equal to constant. So here you can follow that del t by whom del v at what s is equal to constant is equal to minus of what del p upon what del s at what v is equal to constant. So this is your first Maxwell equation. This is your first Maxwell equation. Okay. Similarly, if I remember this equation, TdS is equal to what? dH minus VdP. Then can I write down dH is equal to TdS plus VdP? Yes, I can write. Then let us now again fix it into this one. Like we are following this formula again. Then what I can write that del m by del x. Here your m is what? T. So delta t and del y. Y is what? P. So can I write down delta t upon delta p at what? S is equal to constant is equal to delta v upon what? Delta s at what is equal to constant? Your pressure is equal to constant. So this is your second Maxwell equation. And where do we get third and fourth? So just now we have seen Gibbs function and Helmholtz function. So Helmholtz function was f is equal to u minus ts. U minus ts. Take the differential of this one. Then what you can write is df is equal to du minus tds minus of s into dt. Can I write? And we know that this is nothing but minus of pdv. Can you see du minus tds is minus of pdv? So can I write down df is equal to minus of pdv minus of s into dt? Again, if this is an exact equation, exact differential equation, then how I would write the differential? Delta p upon delta t at what? At volume is equal to constant, and this minus and minus sign will get neutralized. So can I write down this one is equal to delta S upon whom? Delta V at what constant? At temperature is equal to constant. So this is your third Maxwell equation. Okay. And let us move to the fourth one. Then fourth will help to find out the fourth equation, Gibbs function. So we know that G is equal to H minus TS. So again you take the differential, then how you can write down this one as dz is equal to dH minus TdS minus SDT. Can I write? Yeah. Again we know something about this, that TdS is equal to dH minus VdP. This we know, right? So TdS is equal to dH minus VdP. So here we have something in the form dH minus TdS. So this becomes what? Plus VdP. So this is plus VdP. So can I write down dC is equal to VdP minus S into dt? And again, I can write down the fourth Maxwell equation. This is what? Delta V upon what? Delta T at what constant? Pressure is equal to constant is equal to minus of delta S upon whom? Delta P at what constant? Temperature is equal to constant. So these are your four Maxwell equations. Okay. So what these are ordinarily helping you to do? These are helping you to find out. See, if you know the delta T upon delta V when your S is equal to constant, when your entropy is equal to constant, then you can find and you know change in other properties. Got the idea? Like what you are trying to find out is that, let us say that you are interested in finding out what is the temperature change by knowing the changes in other properties, right? So whichever fits the given scenario, you will go to find out that one, and then you will apply. So we know the relationship, like what are the important properties we need to know: temperature, pressure, entropy, and volume, right? So if we know these properties, then most of the property changes you will be able to find out. So we are initially interested in that if I know the changes in pressure, entropy and volume, then can I find out the change in temperature? So this is the idea. So based on the given scenario, how the process has really occurred, you will be able to find out the change in one properties given just by knowing the changes in other properties. So this is how Maxwell will be helping you. Okay. Right. Okay. Let us now move to whom? Joule-Thomson coefficient. What is this? See, Joule-Thomson coefficient, it says that your mu, this is denoted by whom? Mu. This is equal to delta T upon delta P when your enthalpy is equal to constant. So again, question number one, what is the Joule-Thomson coefficient itself? This is a question many times, like 4 5 times 6 times, or you can say even the 10 times. Like if you will count the number of times this question has appeared in various PSU exams, so the number is definitely more than 5. So you should remember what is the Joule-Thomson coefficient, delta T upon delta P, provided your enthalpy is equal to constant. So what is this Joule-Thomson coefficient? Let me help you to understand. See, you are trying to draw constant enthalpy line on what? On TP axis. So if this is your temperature axis and this is your pressure axis, then you are trying to identify what are the constant enthalpy lines, and when we look after, then our constant enthalpy lines are like this one. Okay, so this is your H1. Then if I draw something like this is your H2, so your enthalpy is increasing in this direction, and this is your S3 and like that. So can we see that there is one nature, that this curve has started increasing and then it has got decreased? Yes or no? So there is a point where this change is zero, means that from positive to negative it is traveling. Then what I can say, see, if you try to identify what is the slope in this region, then what is that? That this is, here you will find mu is positive and here your mu value is negative. And if this is S3, this is what? That enthalpy is equal to constant. This is constant enthalpy lines, and when this is drawn, then we can see that this is traveling from positive region to negative region. Then the point where the mu value is 0, we can see that there are some points where your mu value is 0. Then this is called what? Inversion curve. Okay, so again this is a form of question on the inversion curve. Like if I write, then on the inversion curve, everywhere on the inversion curve, what happens? Your mu value is equal to 0. Okay, so let us expand it further and let us try to identify what this mu is helping you to know. See, can I see one thing, that temperature? See, if your mu value is positive, if your mu value is positive, and this is your temperature axis, this is your pressure axis, then what happens? That if you reduce the pressure, if you reduce the pressure, have you seen that what happens? Do you remember that what happens in the isenthalpic process, or we have seen throttling, example of throttling, then we have seen the pressure was being decreased in that region. Do you remember? The pressure was decreased. So if you decrease the pressure, like if you were at this point, or let me draw it with the more visible color. So if you were at this point, and then if your pressure is decreased, like if you have reached till this point, can you see that your temperature has got decreased? Yes or no? Yes. So can I see that when your mu is positive, then if the temperature decrease, then this is called cooling region also. Yeah. Similarly, what will happen that if you decrease the pressure here, then like if you were here and then you have traveled to somewhere here, like this is your next pressure value. So can you see that the pressure has got decreased and temperature has increased? So this becomes what? Heating region. Can you see? So if your Joule-Thomson coefficient is negative, then you can simply say that you have reached to home heating region. And if your Joule-Thomson coefficient is positive, then you are in cooling region. Okay. Now, what about the ideal gases? What about the ideal gases? Let us talk. So for ideal gases, for ideal gas, what happens is that this mu value is 0 everywhere. Okay. Then what will happen that for ideal gas, if mu is 0, then you are along which curve? Along the inversion curve. So if you are working with the ideal gas, then you are always along which curve? Inversion curve. Important. Then the question is that you achieve any heating or cooling? No. Why? Because if you throttle this one, then instead of being cooled, this will get what? Increased. Its value means the temperature will get increased. Then your instead of getting cooling, you will get the heating. Like what I am telling you is that can I use throttling for the case of ideal gas in order to decrease the temperature? The answer is no. Why? Because its Joule-Thomson coefficient is equal to 0, and if Joule-Thomson coefficient is equal to 0, then if I try to what? Throttle it, then what would happen is that even instead of giving the cooling, this will give you heating region. Okay. One thing, right? And one more thing is that can you see that for ideal gases, if I draw this is T and P, for ideal gases, what happens that the entropy is the function of, oh sorry, enthalpy is the function of temperature only. Then what is the isenthalpic line? This one, right? So you would receive no cooling, or rather there will be chances of being heated. Okay. So for ideal gas, we have seen now that the enthalpy is function of temperature only. Then what is the enthalpy curve on TP? We can see that this will be a straight line. Even though you have decreased the pressure, then what happens with the temperature? Your temperature remained constant. It can remain constant, or even it can give you the increased temperature. This is the thing we need to keep in our mind. Okay. Okay. Let us now move to whom? Clausius Clapharon equation. What is this? That this is helping you to find out the enthalpy change associated with the phase change just by measurement of pressure, temperature and volume. So what did I say? That this is helping you to find out enthalpy change find out enthalpy change associated with whom? With phase change. With phase change. Okay. Means phase change is, what is the enthalpy in phase change? Is the latent heat, right? Latent heat by measuring whom just pressure, temperature and volume. So if we know the changes in this one, then we will be able to find out what is the enthalpy change associated with whom? With the phase change. So let us look after that what is this equation. So we know one of the Maxwell equation. What is that Maxwell equation? If you can see that one equation was delta P upon delta T when your volume is constant is equal to delta S upon delta V when your temperature is constant. Let us see that if we have seen or not. Can you identify somewhere here? Your third Maxwell equation. Can you see delta P upon delta T when your volume is constant is equal to delta S upon delta V when your temperature was constant. So let us try to understand what I'm trying to say. Okay. So what is it helping you to find out enthalpy change during the phase change? So let us first try to draw some phase change process here. So here we have fluid region and here we have gas region. So can I see that during the phase change process, the pressure is function of whom? During phase change, here I am writing, during phase change, what we have seen is that the pressure is function of whom? Temperature only. Yes or no? The pressure is function of temperature only. Then can I write down this partial differential as the full differential? So can I write down this one as dP upon dt? Yes, I can write dP upon dt. Okay. And similarly, can I write down this one delta S upon delta V when your temperature is constant? That means automatically your pressure is also constant. So can I write down this one directly as this one, and delta S upon delta V nothing but this is ds upon dV. So your partial got converted into what? Ordinary differential equation. Okay. So using these two, we can find out the enthalpy change. Why? Because if I can write dP upon dt is equal to ds upon dV, and what is the ds? ds is nothing but Sg minus Sf. Yeah, we are talking specifically for whom? Phase change process. So can I write down ds as Sg minus Sf, and similarly Vg dV as Vg minus Vf? We can write. Okay. And we have seen that this volume, see, in gas phase the volume is very higher, specific volume is very higher compared to your volume in fluid region. Okay, specific volume I'm talking about. Okay, so can I write down this one, this difference directly as this is equivalent to Vg? So now your equation dP upon dt is equal to Sg minus Sf, Sg minus Sf upon Vg. And we have also seen that ds is dq upon t. Do you remember? So what is the dq in what is the dq in enthalpy change? What is the dq in enthalpy? Phase change. dq in phase change is nothing but the change in enthalpy between these two. Yes or no? We are talking about whom? Phase change region. Like if this is your ts axis, then we know that what is the heat supplied in this region, dq is nothing but the enthalpy change. We have seen this also, enthalpy change. So what is enthalpy change here? Enthalpy change, can I write down Sg minus Sf is equal to what? ds, and ds is dq upon t, and dq is Hg minus Hf upon t. So in short, I can write down this one as HFG. HFG, that means latent heat of evaporation divided by T. So can I write down this one now directly as HFG upon T into Vg? So this is your Clapharon equation. Can you see that just by knowing the change in pressure, temperature, you are able to find out, and the volume, you are able to find out what is the enthalpy change. Can you see? Yes. Yeah. So this is what your Clapharon equation is helping you. And now if your vapor is ideal gas, like if you consider vapor as ideal gas, then this equation will be sorted to whom? Like we know that PV is equal to RT. Why I am writing RT? Because I have written V as specific volume. Specific volume is volume per unit mass. Okay. So now, can I write down Vg is equal to RT R into Ts upon Ps? Ts is saturation temperature, Ps is saturation pressure. If I can consider vapor as an ideal gas, then what I would do is that Vg is RT upon P, and T is what? Saturation temperature, Ps is the saturation pressure. So this is equal to what? This HFG is nothing but latent heat. So I can write down this is latent heat, right? Divided by T we already have, and T is here what? Saturation temperature only. And let us replace Vg by whom? RTS upon PS. So can I write down this one as R into 1T we already had, right? So we can write down Ts square, and this Ps will go on what? Numerator. So this is Ps. So this equation dP upon dt is equal to latent heat into Ps, means saturation pressure, divided by RTS square. This is called Clausius-Clapeyron equation. I hope you got it. Okay. And so then you would be asking me that what is the difference between like why we are deriving it? Like Maxwell could have also done this, right? So Maxwell is also helping us to do the same, but this is one just further extension of those equations. Okay. So Maxwell equations are used to finding out what? Entropy change by measuring pressure, volume and temperature. So like Clausius, Clapeyron helping us enthalpy change with the phase change. But if this was not, if we have not reduced it into what? Some desired form, then if this was a Maxwell equation, then Maxwell equation, it is helping us to find out what? Find out entropy change, entropy change by what? By changing, by finding out the changing, by measuring which things? Pressure, volume and temperature. Right? Here what we can do, enthalpy change for phase change, when we can know the what? The changes in pressure, temperature and volume. Okay. Now let us now understand few things about ideal gases. Okay, this is very important to know the properties of ideal gases, and more specifically mixture of ideal gases. Very important. Many a times we have seen the questions on this area. So let us try to solve mixture of ideal gases. Mixture of ideal gases. So let us understand few gas laws. Very important, very important, I would say. That let us understand few gas laws. So in short, I would be writing that what is that particular gas law. So one law we must have heard, that Boyle's law. What I am helping you to find out is gas laws. Before moving to the mixture, let us understand some gas laws. Okay, so first gas law is Boyle's law. So I'm just writing in the symbolic form. Boyle's law says that it will help you to find out the change in volume when you are working at temperature is equal to constant. That means if your temperature is equal to constant, then your Boyle's law says that volume is inversely proportional to pressure. Got the idea? That if your temperature is constant, this is not the ideal gas law. This is just simply Boyle's law and applicable to anyone. Got it? The Boyle's law, this is applicable to anyone. So the Boyle's law, Charles law, and Avogadro law, gas law, these things will help you to whom? Will help you to deduce to what? To deduce to ideal gas law. But if I say that, can I apply this Boyle's law to any gas? Yes, we can. Okay, so this is Boyle's law. Boyle's law says that if your temperature is constant, then volume is inversely proportional to pressure. Okay, then what is Charles law? Even though we know this, like we know this fact from PV is equal to MRT, right? We know this fact that if the temperature is constant, then I can say that the volume is inversely proportional to pressure. But we have reduced to this fact using these experiments only from Boyle's law, Charles law, and what? Gauss-Lussac law. Okay. So Charles law says you that if your pressure is constant, if your pressure is constant, then your volume, here you can see that if your pressure is constant, then your volume is directly proportional to whom? Temperature. Got the idea? This is, it says that if your temperature is constant, volume is inversely proportional to pressure, and in the Charles law, your volume is inversely proportional to temperature. So these are helping you to find out what is the change in volume if you know what the change is in pressure. Okay, and then we have Gauss-Lussac law. This law says what? That if your volume is equal to constant, then your pressure is directly proportional to whom? Temperature. Like if your volume remains constant, then the pressure will change in pressure will be dependent upon temperature. So can you see that these laws, nothing but these can combine into what? Ideal gas law. We can see. Okay. And the one also very important law is called Avogadro law. So what this law says you that for ideal gas, now this is for ideal gas. So this says that for ideal gas, it says that the volume divided by what? Number of volumes, number of moles, this is constant. What does it mean? That if you increase the volume, like if you increase the amount of gas, how do you increase the amount of gas? By increasing the number of moles? Yes or no? So if you increase the number of moles, then your the volume will also increase. This law says that if we increase the amount of gas, the if we increase the amount of gas, then volume also increases. Very important laws. So sometimes in the PSU exams, we have seen that they will ask you simply the gas law. So we should know that Boyle's law was dedicated to whom? Temperature is equal to constant. Or we can also remember in terms of volume that Boyle's law relates volume with whom? Pressure. So in short, we can remember that BP means blood pressure. So we can relate that Boyle's was related volume to whom? Pressure. Then Charles' law is relating volume with whom? T. So CT and BP words are like CT scan words we have seen, right? And BP word. So we can relate that. Okay, here the volume change was related to whom? Pressure. Here the in the Charles law, the volume change was related to whom? Temperature. Okay. And this Gauss-Lussac law is obviously for volume is equal to constant. So here your pressure is directly proportional to temperature, it has been said. And then Avogadro law, this is for ideal gas. Okay. Now there is one very important law called Dalton's law of partial pressure. What this law says is, this law says you that, let us say that you are having a mixture of n number of gases. Then let us say that there is a container, okay, and then here you have n number of gases, let us say hydrogen, oxygen, helium, nitrogen, and various other gases. Then it will ask you that what is the total pressure of this chamber? What is P total? Okay, so this is the law helping us to find out partial pressure. It says that total pressure will be equal to the sum of individual pressure of the gases. So what I would say is that P total will be equal to sum of, let us say that there are n number of gases, then P1 plus P2 plus P3 summation till whatever, let us say that there is oxygen and hydrogen, then P total will be the sum of the pressure of hydrogen and plus sum of the pressure of oxygen. So this will tell you, and this is what? This is partial pressure of, this is partial pressure. Partial pressure means what? That individual gas on pressure. Okay, so that is partial pressure, right? So let us understand it bit further. Then what I have written is that the total pressure is the sum of individual pressures, right? So can I write that P1 is equal to P1, and see here the volume we have always taken about whom? The volume of the container. We have never talked about the individual volume, right? So what I can write here is that, let us say the gas number 1. So P1 into V is equal to N1 P1 into V is equal to N1 is its individual number of molecules into gas constant, universal gas constant into T. The temperature and volume will be the constant, will be same for all the individual molecules. Then can I write down P2 into V is equal to N2 into R bar T, and like that for any gas, for all of the gases. Then when I take the sum, then can I write down this one as P1, like I am taking sum of left hand sides and right hand sides, Then can I write down P1 plus P2, P2 till Pn into what? Volume is equal to, can I write down here that this is nothing but R bar and T is common, and then can I write down this is N1 plus N2 plus N3 and like that, right? Means N3 till N of N. This is right. So can I write down this one? This is nothing but total pressure. Just now we have seen that this is the Dalton's law of partial pressure. So can I write down this is P total into volume. This is equal to nothing but summation of N, right? Summation of number of molecules into what? R bar into T. R bar into T. So this is, let us say that this is equation A, and let me say that this is equation 1. Then if you do 1 upon A, then what you can see is that 1 upon A is P1 into V upon PT. This is equation A. Okay. So PT into V, yeah, this becomes equal to what? Here R bar T is common. So here we have N1 upon summation of N. Yeah. So can you see that one very important relation, that P1 upon PT? Why? Because this volume are same, right? So this got cancelled out. This is equal to nothing but N1 upon summation of N. So this is what? This is nothing but mole fraction. Okay. So mole fraction. So if you know the individual mole fractions even, then you can find out their partial pressure. Like let us say that if you know the mole fraction of the molecule 2, like gas 2, then you can find out that what is its individual pressure. If you know the total number of mole fraction, if you know, then you are known with the number of molecules also, if you know total pressure and all. So this is also an important relation. Let me mark it important. Okay. One thing is Dalton's law of partial pressure. This is also important. So using this equation, we can apply it to various other properties also. So let us say we are interested in finding out that what is R equivalent. Like we know we have written in terms of R bar, like universal gas constant. If I wish to find out write in terms of characteristic gas constant, then I could have written this P1 into V is equal to M1, means the mass of that particular gas, into R1, means R of that particular gas, into T. Similarly, we could have written P2 into V is equal to M2 into R2 into T. Similarly, for any gas, we could have written P3 into V, M3, R3, T. So again, you take the sum of these three, like all these equations. So can I write P1 plus P2 plus Pn into V is equal to, now I will be able to write down that this is nothing but the M1 R1 plus M2 R2 plus M3 R3 till what? Mn Rn multiplied by whom? Temperature T. So can you see that this is again nothing but total pressure? So can I write down this is total pressure into V is equal to, this is nothing but summation of mass into R. So can I write down this is summation of mass into R multiplied by T. Okay. Can I write this one? And now let us write down the whole gas equation, means the mixtures equation in terms of equivalent moment. Equivalent what? Characteristic gas constant. Then can I write down that pressure total into volume is equal to total mass multiplied by whom? Total mass means summation of mass multiplied by whom? R equivalent into T. Can I write that total pressure into volume is equal to summation of mass into R equivalent into T? this would look like this one only, right? So now we have two equations. Then if you compare these two equations, then can you see that this R equivalent, like can I see one thing, is that R equivalent is nothing but summation of MR upon M. Yes or no? Like summation of MR upon M becomes R equivalent. So R equivalent, like you take the ratio of these two, then what will happen? That R equivalent, like if you say this is 1 and this is 2, then 1 upon 2 would reduce to whom? That PTV got cancelled out. Then R equivalent is left with whom? Summation of MR upon M. So can I write down this one as summation of M into R divided by summation of M? What is this M into R? Means here summation of M into R means what? That you will take the product of M into R of all the individual gases, and then you take the sum of that, and then you divide it with the whole mass, then you will be able to find out what is R equivalent. This is an important relation. So this similar relation can be extended to whom? What is CP means specific heat equivalent, and similarly what is the specific heat equivalent at constant volume and constant pressure. So here what you would do is that this will be nothing but the summation of mass into whom? Cp divided by summation of mass. Here this will be equal to summation of mass into Cv divided by whom? Summation of mass. So this is very important relation. We should keep this thing in our mind. Okay. These are important relations, right? Okay, now. Then we sometimes they will ask you that tell me that what is equivalent molecular mass. Like we have seen equivalent what characteristic gas constant, we have seen equivalent specific heat at constant volume and all. Then we will have to find out sometimes that what is equivalent molecular mass. So molecular mass is nothing but, we know that what is summation of masses. This is nothing but m1 plus m2 plus till mn, right? Mn. Then we have summation of n into molecular mass is equal to, mass equivalent will be the mole of 1 into what is that individual mass. Similarly, the number of moles into the molecular mass. This is nothing but the equivalent mass, right? The number of moles into that particular individual mass. This is what? Molecular mass, right? So can I see that equivalent molecular weight, this is nothing but n1 upon summation of n into m1 plus n2 upon summation of n into m2 till summation of n upon summation of n into mn. Then what you can see is that this is nothing but mole fraction. So mass equivalent is nothing but mole fraction of that particular gas multiplied by whom? Molecular mass. Similarly, mole fraction of that particular gas multiplied by whom? Molecular mass. And if you follow this, then you will be able to find out that what is equivalent molecular weight of that particular gas, like the mixture of gases. Like we have various scenarios where we will be not working with one gas, but we will be having mixture of gases. Then how do you know the behavior if unless you know that what is equivalent pressure, what is the equivalent characteristic gas constant, not universal, characteristic gas constant, what is equivalent molecular mass. So you should know these things, right? Okay. Now, then there is one important factor called compressibility factor. What is this factor? It says that you know ideal gas equation, right? So it says that PV is equal to MRT, this we know, right? So this is trying to depict you that PV upon RT. PV upon RT, this is like if I take in terms of specific volume, then can I write down P into specific volume upon V upon M is specific volume, right? So can I write down PV upon RT, right? And for ideal gas, this is equal to 1. Can you see that this value is equal to 1? So for what about real gases? See, this is the thing called compressibility factor. So I define compressibility factor as this is PV upon RT. Then what is known to us is that this Z value can be less than 1, it can be greater than 1, and it can be equal to 1 also. So the compressibility factor is equal to 1 for whom? For ideal gas. For ideal gas. And for real gases, for real gases, for real gases, for real gases, what will happen is that this can be less than 1 or greater than 1. So this compressibility factor is helping you to understand that how closely you are approaching ideal gas. Like if Z is equal to 1, then you are behaving like ideal gas, and if Z is not equal to 1, then you are not behaving as ideal gas. Okay. Then different gases are behaving different at different pressures, but there is one experiment. Then we concluded that if I reduce them to one pressure called reduced pressure, and one thing called reduced temperature. Okay, so what is this reduced pressure and reduced temperature? Is like, see, different gases, listen to this statement, like different gases will be behaving different at the same pressure, yes or no? Let us say that we are having hydrogen, we have having nitrogen, so this will behave differently on the same pressure. Why? Because we have seen that PV is equal to MRT, and here we have seen that we have R thing which can take care about that. Even though you are at same pressure, then your molecule can behave differently, right? So their behavior are different at the same pressure for different molecules. Then it says that all the molecules will behave same when you are working at reduced pressure and reduced temperature. Then what is reduced pressure? Reduced pressure is PR is P upon P critical. Okay, and similarly, what is T reduced? T reduced is means temperature reduced is whatever is the your temperature which you are willing to work, and divided by T critical. So P reduced is P upon P critical, and T reduced is T upon T critical. Okay. Like what is this? That let us say that you are working with gas A and gas B. Okay, and your gas A is at, let us say, 5 bar, and its critical pressure, let us say that this is 2.5 bar. Okay, and let us say that we have gas B which is at 4 bar, and the critical pressure of this one is 2 bar. then can you see that the P reduced value is 0.5 for both of them, right? So if you are able to find out P reduced and T reduced, then you can say that, okay, the gases would behave same at these reduced pressure and temperature. So based on this, we have one thing called compressibility chart. Compressibility factor we have seen. So now we will draw what? Compressibility chart. Compressibility chart. So what is this compressibility chart? It is drawn for whom? Here you have compressibility factor and here we have P reduced. And then obviously here we will be having what? Temperature is equal to, here what we will be having? T reduced lines, constant TR lines. Got the idea what is compressibility chart? Here we will be having, sometimes they would ask you that where it is drawn. So with it is drawn like on what axis? One axis is compressibility factor and the second one is what? Reduced pressure. So between these two we have drawn what? Compressibility chart. Got it? So this compressibility chart is what? That you will be drawing constant TR lines. So how it behaves like that? The curve looks like, these are your constant TR lines. So you have started from, let us say that if you are at ideal gas, then your Z value is 1. Okay. So you have started from this point and then your PR and TR. So your TR, constant TR values you are trying to draw, and the other one would look like something like this, that it has come to this point and then it has what increased. So this is what? This is your TR. Let us say that this TR is equal to 1. Then this TR is equal to 1.1 and like that. Okay. So we have TR increasing in this direction. Right. So this is enough information we should hold, that let us say that if you are working with any gas, like if you are at these axes, like if you are at TR is equal to 1, then if you know the behavior of one gas, then you can say that all the gases, if they are at this TR value 1, then I can say that all the gases behavior is known to me. Got it? So this was about whom? Gas laws. And then we have one equation called van der Waals equation. See what happens in your ideal gas. I have initially told you that two things were neglected. One thing was that the container volume was taken care, molecules volume we were not taking care, and the intermolecular forces were neglected. So van der Waals is the one who is taking care of these two things. Then he gave the equation that P is equal to means P plus A upon V square into V minus B, V minus B is equal to R bar into T. Initially, what do we had is that PV is equal to R bar T. So what is we can see here is that we are taking care of intermolecular forces minus we are subtracting whom what? The molecule's volume. So this is accounting for whom? This is accounts for, this accounts for what? Accounts for volume occupied by whom? By gas molecules. Okay. And this is taking care of whom? This accounts for intramolecular forces. Yeah. Then these A and B are mostly constants, okay? And this is not important to remember, but if you can like just know that what are the variables it are inculcating, then this is 3 critical whole square divided by 64 into P critical. This is your A value, and your B value is R into T critical divided by 8 into P. Okay. So this was about van der Waals equation. And then we have few other equations of state. So one of them which we have seen variously asked is virial equation of state. So what is this? That P is equal to RT upon V plus AT upon V square plus BT upon VQ. It says that A is function of temperature, CT divided by V to the power 4 and like that. Okay. So these are functions of whom, like they might ask you that they will give you this equation and they will ask you that what are these A, B and C. So these are coefficient which are dependent upon temperature. So this is, we are trying to express this equation in terms of what? In terms of series. In the series form. Yeah. So this is all about like what areas we should cover for PSU or even for GATE exam. So we mostly we will not be facing very rigorous numericals, like numericals are very like less calculative, so we need not to be worried about that part also. And there is two coefficients only, you need to know what are these coefficients, and that is it. This huge derivation before it, then the derivations are not important as of now. So I am helping you to write down two coefficients. One is thermal isothermal compressibility. Isothermal compressibility denoted by whom KT is equal to, it says you that you, if you are compressing some gas at what or any substance, you are compressing it with any compressible substance. If you are compressing it what, at constant temperature, isothermal, then this coefficient is equal to what, that you are compressing at constant temperature, then you are changing what, pressure independently, right? So you are handling temperature, then you are trying to compare it with change in pressure, then this is equal to minus of 1 upon V. This is your isothermal compressibility factor, Kt, is minus of 1 upon V. This is nothing but the change in volume upon what is the change in pressure at the constant temperature. Okay. Similarly, we will be having coefficient of volume expansibility. This is compressibility. Then we have coefficient of volume expansivity. This is denoted by beta, and this is equal to 1 upon V into, now you are compressing it with respect to whom? With respect to change in pressure. So no, this is the coefficient of volume expansibility. Like if you are expanding your volume, then what is the coefficient which will help you to determine this? Okay, so this is your coefficient of volume expansibility. Only the remembrance of this one would help. There is huge derivation, but not required as of now. Okay, so we should know these two. Only the trick to remember is that when we are working with isothermal, then we are taking temperature as constant, and then we have the change in V with the change in whom? Pressure, and then we are dividing it minus 1 upon V. Why minus sign? Minus sign because when you are compressing your delta V, this value will be negative, right? Then this minus sign will take care of that, this will become automatically positive, right? And here we have 1 upon delta V, and then we are taking care of whom? Constant pressure. Like at the same pressure we are changing, we are looking after that with the change in temperature, what will be the change in volume, right? Okay. And then we have seen this now, that Cp minus Cv is equal to R. This we have seen earlier. Okay, so here what happens, that there is again one derivation called Cp minus Cb. This becomes equal to T into V. Beta, just now we have seen what is beta, upon Kt. Okay. So this is called Mayer's equation. Then can you see that this constant, this is nothing but R value? Yeah. Why? Because Cp minus Cv is equal to R now. Then Cp minus Cv is Tv beta square upon Kt. Then this is nothing but trying to show the R value for whom? For ideal gases specifically. Okay. Okay. So this is all about your thermodynamics syllabus, like which has been basic thermodynamics, where we have seen that from this area we have seen various questions. So we have tackled most of those areas where questions are keep on coming, and moreover we have covered the whole syllabus, but the question part we have focused upon those questions which have higher chances of appearing directly into the exam. So let us now go to whom, like let us now try to solve some questions based on this area. Like we have studied properties of pure substances, and we have also seen thermodynamic relations. So these two we have merged into one topic, and we have some questions based on these areas. So let us try to solve those questions, and then we are finished with this term. Okay. Now, so let us go to the question part. Okay. So quickly we'll be solving. So it says that the equation which perfectly represents Gibbs phase rule for a process where the pressure is also a variable is expressed at. So Gibbs phase rule, do we remember we have seen Gibbs phase rule? What was that? P plus F is equal to C plus 2. So find out which one is the answer. P plus F is C plus 2. So here we can see is that P plus F will be C plus 2. Okay, next question. See, the question will be very simple. Like if you follow the lectures, none of the questions will be difficult for you. So just now we have seen that mu was Joule Thompson coefficient. What was that? Delta T upon delta P when your H is equal to constant. So this TP up delta T upon delta P when your H is constant. Then we have Clausius Clapharon equation gives the slope of the curve in Very simple. Where we have seen this one? The Clausius Clapharon gives the slope of the curve in which diagram? HS diagram. Do we remember? No. This is Clausius Clapharon, right? So Clausius Clapharon, yeah, PH diagram. Yeah, PH diagram is correct option. Na? Why? Because we have seen that dP upon dt. If we remember, dP upon dt we have written is that hfg into p upon rt square. We remember. Then it gives the slope of the curve in which diagram? It gives the slope of PT curve. No, this PH is wrong. This is PT curve, right? dP upon dt. So which diagram? This is PT diagram. Okay. Next question. Select the correct statement as per Chance law. So only we will remember what? That for Boyle's law was relating volume to pressure. Chance law was relating volume to whom? Temperature. So let us find out where we can see as per Charles' law. So Charles' law was relating volume to the temperature. So V upon T, wherever we will see V and T, then we will stop. So PB is constant, no. P upon V constant, no. T upon P constant, no. So by option elimination itself we have solved. Why? Because we saw that the Charles' law was relating volume to temperature when your P was constant. See. Next question. Which of the following relations defines Helmholtz function? Which one? Helmholtz function was f is equal to u minus ts and Gibbs function was g is equal to h minus ts. So f is equal to u minus ts, f is equal to u minus ts. Specific heat of monoatomic gases. What happens with the monoatomic gases? Specific heat increases or decreases? Can you recall? See, a specific heat, it is the ratio of gamma. No, specific heat of monoatomic gases we have been asked now. So we have seen for gases. Can you recall that? Specific heat for, you are not telling me options. So have you not gone through? You are not revising. We should revise, otherwise how we will solve? For a specific heat for monoatomic gases, we have seen that does not depend on change in temperature. Can you recall that we have seen that Cp and Cp values were remaining constant when we were changing temperature, and it was increasing with the change with the increase in temperature for whom? For diatomic gases or non-monoatomic. See, questions like this one will always only appear, but if you are not following, then this is the matter of concern. Now, a positive value of Joule-Thomson coefficients of a liquid means, tell me what is the correct option. Just now we have seen when we were having positive value, then can we recall that when this was the curve, then here we have positive slope, here we have negative slope, then temperature drops. Very good, your temperature will drop during the cooling. Why? Because this was the cooling region and this was the heating region. Okay. Now, a fluid behaves as an ideal gas provided it is at what? What was the favorable condition for ideal gas, if we can recall? What was the favorable condition for ideal gas that we are at high high temperature and low pressure. We were at high temperature and low pressure. Yeah, which is the condition? This one. According to Dalton's law, the total pressure of the mixture of gases is equal to sum of the partial pressure of all. Just now we have seen the Dalton's law. So what does it say is that Dalton's law, yeah, sum of the partial pressures of all. See, they will deviate the options by changing some keywords. So it has says that the sum of partial pressures of all divided by average molecular weight. No, wrong. So in order to avoid confusion, just recall what you have studied. What was the form you studied, and then you try to what? Apply in the given options, right? Next question. The ratio PV upon RT is, what is this ratio? Z is equal to PV upon RT. We have seen this is compressibility factor, and this value is equal to 1 for whom? Ideal gases. Okay. Now, it says that generalized compressibility chart is drawn between, if we can recall, here we had compressibility factor, here we had reduced pressure, and then we drawn for whom? TR is equal to constant lines. So we have compressibility factor on y-axis and reduced pressure on x-axis, right? Reduced pressure on x-axis, right? And y-axis compressibility factor on z-axis and reduced pressure on x-axis. See, they have played with the option like on the axis also. These two options are same, but they have changed that compressibility factor is on x-axis. Can you see? So this option is wrong. Okay. And then they have said that the TR on x-axis, TR on x-axis. Then we remember that the TR is equal to constant curves were drawn. Then this was definitely between whom? Z and PR. Okay. Next option. During melting, the volume of pure substance other than water, what happens? During melting, the volume of pure substance other than water, what happened if you remember? For other substances, what happened? We have seen now for general substances, we have seen from liquid to solid. For general substance, what happens? Liquid to solid contract, right? And solid to liquid expand. So it says that volume of pure substance other than what is during melting. So if you have melt, then you will what? You will expand. What will happen that you will increase. Yeah. Okay. Next question. On Euler chart, slope of an isobar on HS diagram is equal to what? HS diagram, what we have seen that HS diagram, yeah, dH upon ds, we have seen it was T. Okay. How? TdS was dH minus VdP, and this dP is constant. Then we have seen that dH upon ds is equal to nothing but T only. Okay, this option. Next. If the degree of saturation of air is 0, the air is said to be. If the degrees of saturation was 0, then do you remember that if degrees of saturation was 0, then this is saturated air. Why? What was the degree of superheat or degree of subcooling? Is that we took the temperature difference between the saturation temperature and here. So if this was the degree of subcooling and this was degree of superheat. So if the degree of saturation is 0, that means you are lying here and here. So what is that condition? This is saturated and this is subcooled. So this is called subcooled and this is what? Saturated. This region is subcooled, this is saturated and saturated. Okay. Next question. Which of one of the following parameters is significant to ascertain chemical equilibrium? Gibbs function. Okay. Nothing to tell now. I told you that what is this equation known as whom? Van der Waals equation. Yeah. The specific heat at constant pressure is defined as specific heat at constant pressure. So you need to take the slope of what curve so that you can find out. See, let me help you to understand how to solve this question. See, H you have seen that H is equal to mCp dt we know. Yeah. So what is Cp here? Or dH we can see now that dH is mCp dt. Yeah. So what will happen? Cp is nothing but dH upon dt when you're right? This is known as what? Just now we have seen this is an periodic. So these are the questions directly taken from some PSU exams, some state engineering services, some engineering services like Indian engineering services we have now, engineering services examinations. So these all questions are taken from those areas. So you can appreciate the fact that the most of the questions like whatever we are solving now, then we are not worrying much. Like we just recall our whatever we have done till now and then we are able to do. So if you follow these lectures, then definitely this will benefit you to solve the questions appearing in the exam. Why? Because like if you know like most of the previous year questions if you have solved, then in the coming year what you would see is that the questions like the questions are not getting exactly repeated but the essence are same. Yes or no? Yes, every time. So this is how it will be helping you to solve the questions appearing from which area? From thermodynamics section. So please revise it. If you have like if you have started your revision, then you should probably start revising it. Follow these ones and definitely you will be able to solve most of the questions appearing in the exam. Okay. Okay, so this was all for like thermodynamics part, and then we will do one lecture on applications part, right?